Hello, and welcome to your official first lecture, which is about minerals. So what is a mineral? A mineral is a naturally occurring, inorganic solid that possesses an orderly crystalline structure and definite chemical composition that allows for some variation. What is naturally occurring but inorganic? Inorganic means it has never been alive, meaning that sugar and coal are naturally organic occurring compounds because they come from something that was alive. Sugar comes from sugarcane, coal comes from decaying old plants, right? That have gone under pressure and heat. And there's multiple types of coal, but generally it comes from plants that are from the Jurassic, Triassic, and before. So naturally occurring means it occurs in nature. We don't make it. Inorganic means it was never alive. Okay, so that's very important. Minerals are also made up of elements, and so atoms. Okay. The variation in minerals that we talk about is what we call replaceable parts. Okay. This means that the mineral's chemical formula has some elements that can alternate, meaning that these elements have, or their atoms have a similar valence so they can replace each other in the chemical composition, such as potassium and sodium in the rock feldspar, or the mineral feldspar. So some minerals are made up of only one atom, like gold and sulfur. So on the right top, we have gold, and this is hydrothermal gold. It's really cool. It gets deposited by hydrothermal waters, and we find this, it's called native gold. We also have native copper and silver. And on the left, we have two different types of sulfur. One is more crystalline, and the other one looks more like just powder that's been compressed into a big piece. So on the top, we see that this is what we call a massive piece of sulfur, whereas on the bottom, we can figure out some sort of crystalline form. Other minerals, though, are made up of multiple elements, such as olivine, which has magnesium, iron, and silica. And this is the green element in here. The black stuff is actually basalt. It's old lava, hardened magma or lava. Olivine, some of you know as peridot, which is a gemstone. And it's a very rare gemstone because it's really hard to find olivine in gemstone quality, big enough that it looks like that. So minerals will actually come together to make up rocks like granite, which we see here. So in here, we're going to have things like quartz, biotite. We're going to have some feldspars. We're also going to see muscovite in here. So muscovite and biotite are very similar. They're two different types of mica, and we can see both in here in the form right here, where it looks a little bit goldish, and right here, this is biotite. And then in here, we're also going to have different pieces. So over here looks like it's going to be something called feldspar. And over here, we're going to see quartz. Quartz is going to be a little bit more translucent depending on which angle you look at it at. Okay, so things to remember about a mineral. Minerals are naturally occurring. They occur in nature without our help. Minerals are solid. Never are we going to have a liquid mineral, which is great because ice is technically a mineral, but water is not. Minerals have a definite chemical composition, okay? Atoms that make up minerals are arranged in an orderly pattern, which causes them to form crystals. And lastly, minerals are inorganic. They were never alive. So the study of minerals is known as mineralogy. And minerals have been very important in human history. We've used flint and chert, which are both types of quartz, for weapons and tools. They are what we call microcrystalline quartz. It's quartz that's so tiny that it's not translucent anymore. And this is where we get things like jasper. Gold, silver, and copper were mined by the Egyptians. We see it in use with the Aztecs and Mayans. We use gold and silver and copper as currency for the longest time. Bronze was developed by 2200 BC, and mining became very common in the Middle Ages. So, crystalline structures of minerals. Minerals are made up of elements, atoms, and atoms will come together with different types of bonds. You have ionic, covalent, metallic, van der Waals, and hydrogen. Okay. These chemical bonds allow the element to come together into a tetrahedron and lattice structures. So ionic bonds are the most common due to their transfer of electrons, which I'm sure you've learned all about these in chemistry class. So opposite ions will attract to each other for this reason. So a sodium, which will have a plus, will be attracted to a chlorine, which is a minus. Okay, so anions and cations, remember, they're going to attract. And this will cause salt, halite. Okay, the negative in front of an element means it's an anion, where the positive means it's a cation. Okay. And so that negative, that anion, mean it has extra electrons, whereas the cation has less electrons, and so it wants another electron or two to be happy. Okay. Covalent bonds are the strongest bond. They share electrons rather than giving them away. Iron and chlorine both have 7 electrons in their outermost shell, so they will share 1 to get 8 and so be happy little atoms. Metallic bonds are very similar to covalent. Again, they share electrons, but these are very close packed, and it allows for maximum movement and flexibility, which is why metals have what we call malleability. They're bendy, as well as their conductive properties. Van der Waals bonds are the weakest. They hold gases together with a weak electrostatic bond. Hydrogen bonds are also due to electrostatic attraction between polar molecules. However, it is not due to sharing electrons, but they will form a charged region. So examples of these bonds are diamonds have covalent, halite will give you ionic bonds, olivine has a mixture, it's half ionic, half covalent, ice is all hydrogen bonds, and muscovite has a combination of covalent, van der Waals, and ionic. And the way that these bonds work is part of the way that these minerals will break in specific ways. So for example, muscovite, it breaks off in sheets, okay, because it will break in the weakest bonds. So here we're going to have some mineral characteristics due to their bonds. So bonds are really important in the types of characteristics a mineral will have, like how it breaks. Is it transparent? Is it conductive of electricity or heat? How hard is it? A diamond is very hard, it can scratch glass, but talc is super soft. And what kind of shape will it take? All of this has to do with the type of bonds that are in it. Okay, so ions come together, they form an element in a mineral, and it involves how they connect, okay? So you have a hexagonal structure, an octahedral structure, a tetrahedral structure, and a triangular structure. And these are their crystal systems or lattice systems. So lattice systems are the same for specific minerals. So if you can figure out the lattice, you know what mineral it is. But most of the time, you're going to memorize which of these use optics to figure it out for the most part. You're not going to have to do this, so you don't really need to know much about it. But for the most part, these lattice systems are what will create the crystal we see forming. For example, quartz. The way it forms is because of the lattice system that it has. It will always form that way. So think of a building being built, right? At the beginning of the building process, the workers will put up a bunch of metal beams known as I-beams. And this is basically the shape the building is going to take when it's built, right? And this is the lattice system of the building. It is the structure they will build around. So the way that they do this lattice system indicates the shape of the building when it is built. So most skyscrapers or really tall apartment buildings are going to have a very similar lattice structure, okay? It's the same thing with, for example, quartz. Quartz will always have the same lattice structure, and that's what makes it so great for identifying a mineral. Okay, so the atoms in a mineral are arranged in an ordered geometric pattern, crystal structure, okay? Each mineral has a crystal structure that will always be found for that mineral. For example, every crystal of quartz will have the same internal arrangement of atoms. They will always be ordered the same exact way. If the crystal structure is different, we give it a different name. It's no longer the same mineral. So these are going to be examples of our crystal systems on the left in this chart. You're not going to be quizzed on these, so don't worry about it. But minerals have specific shapes that they'll take because of their lattice structure. So minerals will always have the same system no matter what. For example, pyrite or fool's gold will always form in a cube. And then we have crystal habits. So these are the ideal shape a mineral will take that we can identify, like prisms, cubes, sheets. These form with ideal growth conditions. So there are many different types, and in some cases it can be a major identifier, and in others it really isn't. For example, fluorite and quartz. Quartz will form in a prism, and fluorite will form an octahedron, which is like an 8-sided dice. In this case, it's going to be a major determiner between quartz and fluorite, because otherwise these two minerals look very similar. They both can have many different colors. In a big piece that doesn't have a direct shape, sometimes even it's hard to tell the difference. And so one of the things that we can use is if one is a prism and one does this, the octahedron. There are other ways to determine the difference, and we'll go over them in a second. So these are the different types of habits. The first one, we have prismatic, which on the left we have quartz, and we also have tourmaline, which you're going to see both of these in class, okay? So tourmaline is generally black. It's going to have some little bits of color in it, but it makes very tiny little prisms, which we can see right here. And then we have the octahedra habit, which is fluorite, like what here, okay? These, again, are perfect. You're not always going to see fluorite like that. A lot of times you're going to see fluorite in giant chunks that don't have this. Another habit is dodecahedron, where we're going to see garnet. And then we have the lamellar foliated or micaceous. So garnet will generally have 20 sides. There are other versions of dodecahedrons, but we're going to talk about this from a general aspect. So for those of you who are familiar with dice, look up a d20, and that's what it looks like. Okay. For the micaceous habit, which can also be known as foliated or lamellar, but in this case we're going to really stick with micaceous, the name comes from the mica mineral group, where it forms a flat book, which will peel into thin sheets, hence foliated. This is known as a tabular habit as well, where it looks like a big flat shape like a table. The micaceous minerals are also known for splitting into malleable sheets, okay? And so what we see right here is biotite. This is a book of biotite, and it will legitimately just sheet. Like it'll peel into thin sheets, which we can kind of see up here. Now we have the fibrous habit. And an example of that is chrysotile, and we can see right here little fibers peeling off. Okay, and then we have the bladed habit, such as actinolite. So both chrysotile and actinolite are both forms of asbestos. But don't worry, if you get both of these as an example, they won't hurt you. Okay, there's another type of asbestos. Generally, it's the fibrous ones, but they need to be able to break into a powder. Okay, and then another example of bladed is kyanite, which is blue, and it makes these big, more tabular blades. So, and they're pretty neat. They're very pretty. So with bladed, the mineral looks like a bunch of small blades. And you can actually pull them off this way, and it's pretty cool. Generally, they look like they're radiating from somewhere, which is neat. Whereas fibrous, it's kind of like a whole bunch of little fibers packed together. Okay, so acicular minerals appear to look like tiny needles, and many times it's written as acicular radiating because they seem to spray from a specific point. So this is stibnite. This is our example of acicular. And then we have the mammillary or botryoidal, which is very similar. Okay, both are globs of crystal very close together. They fall under the category of coliform. Okay, if it's just one glob, it's called globular, and we'll go over that in a second. But this is smithsonite. This is an example of a botryoidal mineral, and you can see it looks like a bunch of little blobs. Globular is very similar to mammillary, but the blobs of the mineral are very much separated. So you're going to have one glob. Okay, and this is gyrolite. And then we have oolitic, which we see a lot as hematite. Oolitic minerals are crystalline aggregates no more than 4 millimeters in size, and they're a result of chemical precipitation. The other way we see this is calcite, but this is very common in the desert. So dendritic habits is where you're going to see things like native copper, native gold, and native silver, which means it was deposited due to hydrothermal activity. A radiating habit is also known as divergent, and the best example of this is the mineral called wavellite. And this is pretty descriptive, so when you see a yellowish green mineral that is radiating and looks like a whole bunch of little seashells, it's almost always wavellite. Druzy habit means that the mineral is very, very small. The whole surface is covered with these small crystals. Often you cannot see their actual crystal shape without the help of a hand lens. If it's smaller, it would be microscopic or microcrystalline, in which case we would have a mineral like jasper. And then we have geodes, which our example here is calcite. This is a geode. Okay. Geodes form when minerals are precipitated inside of a cavity, but it's not completely filled. Okay, if there has to be a gap for it to be called a geode. So other examples of geodes that we see are quartz geodes, like amethyst. Banded habit is most common in agates. This habit only works when you can clearly differentiate bands either through color or texture, meaning how it feels. And we can see this right here. See this gap right here? If this was open, it would be a type of geode, but because it fully precipitated, it is no longer a geode, but we see this banded agate down here. And then we have the stalactic habit, which is kind of self-explanatory. Generally, it's also going to be quartz or limestone. And this is when a mineral has been deposited either as a stalactite or a stalagmite. And then our last habit is massive. The massive habit is when there is no clear habit, like with that chunk of sulfur that we saw in the beginning. Okay, this is blue chalcedony. This could mean it came from a much larger crystal, which would show the main habit, or it just didn't have the correct conditions to form its ideal habit. You're going to see a lot of minerals that are going to do this. One example, again, is sulfur. Another one is going to be quartz. You'll also find massive pieces of feldspar, galena, hematite, and what's our last one? Fluorite. Okay, that's the other one. So these are the list of habits that we just went over, and I'll put up the definitions for each of them in a PDF document later, and you'll be able to find it. And this is something that you're going to need for the lab as well, because we're going to do a lab on this. So now we're going to get to twinning. Twinning is interesting. Twinning is pretty cool. Rational, symmetrically related intergrowth. That's what twinning is. Basically, it's two mineral crystals that grow together. Okay, so it'll be of the same mineral. So lattices of each orientation have definite crystallographic relation to each other, meaning that it will form in symmetry. So the twin operation is the symmetry operation which relates to two or more parts, like a mirror or rotated. Okay, so the reflection or twin plane is known as the fishtail. And right here we have a gypsum fishtail twin. We can see here that we have two mirrored crystals. So if the twinning is related to two or more parts, and there's a rotation about 180 degrees without an axis common to both, you'll have normal and parallel twins. And the example we have here is called the Carlsbad twin, which we have an orthoclase feldspar showing it. These are the ones that are tending to have them. So we also have contact and penetration twins, which are both simple twins. So there's only two parts. So with penetration twins, the one crystal appears to be going through the other. So we'll see things like the Storolite twins, which almost look like crosses. This is the Carlsbad twin. These guys are just crazy. And then we have contact twins, where they're kind of just growing and touching each other, like the Japan twin in quartz, which also, when you have the whole thing, looks like a heart. And then you have multiple twins, which are two segments repeated by the same law, and then you have cyclic twins, which are successive planes that aren't parallel. So this is a cyclic twin. It makes almost like a flower. And then there's this one, which is a pseudohexagonal twin, and it looks almost like a snowflake. Okay, and then we have polysynthetic twins, which we call the albite law in plagioclase, where you have them forming almost in layers. And this is what that looks like in thin section. And it's cool because when we rotate it, different parts of the mineral will light up, which shows us the type of twinning. So silicate minerals will have silicate in their mineral formula. Okay, so silica is one of the most abundant minerals in the crust along with oxygen. So these two minerals tend to bond, forming a tetrahedron. Non-silicate minerals will have another major element, such as carbon or sulfur, rather than silica in their mineral formula. And this is what a tetrahedron looks like. It's almost like a triangle. So, systematic mineralogy is a description of how minerals are divided into groups, and they will be based on anions. So you have a single anion and an anion group, like silicates. These are then further divided based on their structures. So the divisions, which we're not going to really focus on in here, are class, family, group, series, species, and variety, almost like in biology. So for example, albite is the sodium-rich variety of a mineral species, and the albite is the anorthite series of the feldspar group of the tectosilicate family of the silicate class, because it has SiO. Okay, so remember, class, anion division, family, structural division, group, structural division, series, solid, solution, species, and then variety, which has to do with the replaceable parts. So the elemental composition of the Earth's crust, most of it, again, is oxygen and silica. And this is why silicate minerals are so prominent. Next is then aluminum, iron, calcium, sodium, potassium, magnesium, etc. So silicates are the most common group of minerals forming the Earth's crust, okay? Very, very important, because silica and oxygen are 75% of our crust. So 25% of all minerals and 40% of rock-forming minerals is silicates. 90% of the Earth's crust, these are the minerals you're most likely to find. So silicate systems, you're going to have two different types. All silicate systems have the silicon-oxygen tetrahedron known as SiO4, and the net charge of silicate tetrahedron is 4-. Tetrahedron can share oxygen. When they do, they come together and will form chains, double chains, and sheets. Okay, and then they'll eventually get to a three-dimensional network. So these silicates can bond with iron, magnesium, aluminum, and potassium. So if it's a felsic or light-colored silicate, you're going to have aluminum, potassium, sodium, or calcium. And if it's mafic or a dark-colored silicate, it's going to be iron or magnesium that is paired with the silicate. So these will be connected, again, to these other elements that have a positive charge, like magnesium, iron, aluminum, calcium, potassium. These are what we call replaceable parts. The most common light-colored minerals will have SiO4 mixed with aluminum, potassium, calcium, and sodium, and they'll produce potassium feldspar, plagioclase, feldspar, quartz, muscovite, and clay minerals. The most common dark-colored silicates will have SiO mixed with magnesium and iron, such as olivine, pyroxene, hornblende, biotite, and garnet. These will be found in specific scenarios like metamorphic rocks or igneous rocks, which are both have to do with volcanic origins. So the elements in parentheses here are what we know as the replaceable parts in these minerals. This means, for example, in plagioclase feldspar, calcium or sodium are interchangeable. You can have a calcium plagioclase or a sodium plagioclase. So the other thing we can see here is if we were to do quartz, the quartz color is dependent on what elements can be found in trace amounts, meaning very tiny amounts. So when you have rose quartz, it has trace amounts of titanium. Smoky quartz occurs when you have it exposed to radiation. So if you find a whole lot of that, you should get out of whatever cave you are in because there is probably a lot of radiation in there. Jasper has iron in it, which is why it's red. It's also microcrystalline, so that's why it seems to be solid and not see-through. Opal is another quartz, but it'll have water in its system, and it's also microcrystalline. So quartz and other polymorphs are only minerals with silica and oxygen, okay? Meaning they don't have iron added to it, so it's not an iron silicate, it's just silicate. All other silicates are charge balanced by other cations, which is the glue that holds together the silica tetrahedron. So let's look at mafic versus felsic. Mafic are rich in magnesium and iron, or ferrum. They're silica poor. like biotite, amphiboles, pyroxenes, and olivine. They're commonly very dark. So biotite's like black. Amphibole is pretty much black. Pyroxenes are pretty dark. They can be a green color if they have chrome in them. And olivine is generally a pretty green color, but it's also a darker mineral, whereas felsic minerals are rich in silica and aluminum, like feldspar, quartz, muscovite, and feldspatoids. These are commonly light colored, okay? Muscovite has a goldish color to it, for example. Feldspars tend to be white or pink. So where silicates are 92% of minerals, non-silicate minerals are the other 8%. They generally make up sedimentary rocks, accessory minerals, and ore deposits. These groups are carbonates, halides like salt and fluorite, oxides like hematite and magnetite, sulfides like galena and pyrite, sulfates like gypsum and anhydrite, and native elements like gold, copper, silver. So these are equally as important for trade and industry. So gypsum and anhydrite, for example, their chemical composition is CaSO4 with 2 H2O and CaSO4. So this is where we have gypsum and anhydrite. So what is the big difference between them? It's this, it's water. So halite and gypsum in particular are usually found as thick deposits where there used to be oceans. So salt flats are where halite is mined, for example, and gypsum is found in caves in Mexico. The gypsum caves in Mexico are the largest source of gypsum in the world. So gypsum has water involved, whereas anhydrite has water removed, as in it was deposited without this water. Whereas halides like salt or halite will also have water in it, but we know it as sodium chlorine, right? This is what happens when water evaporates, and this gets left behind. The same thing with anhydrite, okay? Gypsum and anhydrite otherwise are the same exact thing. It's just one has no water. So native elements, or the metals, in their pure form are not bonded to another element. Okay, they are also known as accessory minerals. So the metallics are gold, copper, and silver. Rarely you'll find platinum, mercury, arsenic, and metallic iron, which you tend to find in meteorites. Semi-metallic are arsenic, antimony, and bismuth, and antimony is super explosive, by the way. I'm going to put up a YouTube video for you guys so you can actually see how explosive this is, because it's cool. Non-metallics are carbon, like diamond and graphite, and then you have sulfur. They're all going to be cubic. They all are going to be made of metallic bonds. You're going to have high electric conductivity and high density, especially with the metallic ones and semi-metallic. The non-metallics are going to be a little bit different. They're not going to have those metallic bonds necessarily. Remember, diamond has these covalent bonds. Okay, so diamonds are much harder. It's bonded with covalent. It's close packed, so it's very tight. It forms very deep in the earth under high pressure and temperatures. And the only way they actually come to the surface is during a volcanic eruption. And they won't come up unless the speeds of movement reach about Mach 4. And they tend to occur in kimberlite volcanoes. So we'll find them in kimberlite pipes after millions of years of erosion. It's pretty cool. Graphite, though, is parallel sheets with van der Waals bonds. So they're very different. The carbon has a much weaker bond here. So each atom is linked to 3 other atoms, and it is very easy to break apart, which is why we use it for pencils. Sulfides are dense and usually metallic. In some ways, they have many major ores. They form in compounds such as S2- or S4+, 6+. S2- is smaller than O2-, so covalent and metallic bonding will form sulfides, the S4+ will form sulfites, and the S6O4 will create sulfates. So sulfates are above average density, average hardness, they're soft, light color, good cleavage, soluble, and sometimes fluorescent. And you have things like anhydrite, barite, gypsum, and alunite. The halides like fluorine, chlorine, bromine, iodine, halite, gypsum, and anhydrite, bond with medium sodium, calcium, or large potassium cations. They are associated with sulfites in evaporite deposits, and they're usually soft, often soluble, and have really good cleavage. So what we can see here so far is this. This is anhydrite. It has a very bladed appearance, if you remember what the bladed habit is, versus gypsum seems a little bit more in the prismatic area. So major ionic constituents of seawater and most common minerals in evaporite sequences. You have potassium is really high, and sodium, which is where we get halite, sylvite, anhydrite, gypsum, calcite, and dolomite. These are the ones that we're most familiar with. Dolomite is actually used in concrete making, which is pretty cool. So carbonates are about 200 minerals that are made with CO3 2-. Okay, they will be mixed with OH, fluorine, chlorine, phosphates, and sulfates. We have 4 groups: the calcite group, which is trigonal, the aragonite group, the monoclinic group with OH, and the hydrated carbonates. So carbonates tend to react with hydrochloric acid, meaning they fizz. And carbonates are what store the carbon in the ocean in the form of CO3. It balances carbon dioxide in the atmosphere and climate change issues. So one of the things that we have talked about, or we will talk about, is if all our oceans were to start evaporating, we would set off a process that would involve adding more carbon to the atmosphere, which would increase heat because carbon is a greenhouse gas, so it traps heat, which would then cause more evaporation, which would cause more release of carbon, which is how they think that Venus became the way that it is, for example. So the calcite groups that we know the most are calcite and azurite and malachite. So malachite and azurite are very well known for their very bright colors. Malachite is green and azurite is this beautiful blue, okay, and calcite. But calcite and azurite and malachite are things that you're actually going to end up seeing in here in our class because I'm going to show them to you. So mineral properties is how we identify minerals. We are going to go over these again when we look at our mineral lab, but there are some pretty cool mineral properties out there. So the major properties are luster, color, cleavage, fracture, what we talked about earlier, which was habit, and their streak, which is the color the mineral leaves behind when you rub it on something that is technically harder than it. Additional properties are, is it magnetic? Does it smell funny? Does it taste funny? Be careful with taste. Okay, some minerals are poisonous. If it is a very bright red color, don't lick it, for the most part. Okay, because it could be something called cinnabar, which is very poisonous. And yes, cinnabar, like Cinnabar Island in the Pokemon games, which has the fire badge. Okay, yes. Is it effervescent? Does hydrochloric acid make it bubble? What about fluorescence and thermoluminescence? How does it feel? What is its diaphaneity? Is it piezoelectric? So fracture is how a mineral breaks when it doesn't cleave. So fracture is irregular in most minerals, which is basically uneven fracture. It looks like that. And you can have different types, such as splintery, which looks like this. You can have uneven, you can have crumbly, you can have jagged or hackly. Sometimes it looks fibrous, okay? And then you have conchoidal. This is conchoidal. This is what we see in obsidian. It's also the type of fracture we see in quartz. Quartz is very well known for its conchoidal fracture, in which case it makes little C's. Okay, and this is very important. Conchoidal fracture makes a whole bunch of little C's. It almost looks like broken glass, but as long as you see these little C's, you know it's a conchoidal fracture. Okay, it will also have uneven fracture like this. And then we have some subconchoidal, which kind of looks like that. And it looks almost like a conchoidal fracture, but not quite. So this one's a little bit more difficult to determine, but you'll definitely almost always see conchoidal right away. Okay. Cleavage is very, very cool. Cleavage is the way that a mineral breaks based off of weaker bonds, for example. So here we have our micaceous habit, such as biotite or any of the mica family, and they'll always cleave in what we know as one direction, okay, where it peels off into little malleable sheets. Okay, and then we have two-directional cleavage, like what we see in feldspar, where it will break in two directions, just like this. Okay, and they're always at 90 degrees. Okay, whereas on this side you'll have a fracture. Okay, and then you have cleavage in two directions that are at 120-degree angles, such as hornblende. And then you have cleavage in three directions at 90-degree angles, and they almost make like steps. And this is halite. And then when you have three directions not at 90 degrees, such as calcite, where it's at 75 and it looks almost like a rhombohedron, and we can see that here. And then we have four-directional cleavage, which is what we see in fluorite. It's also what we see in a lot of cubic minerals, such as pyrite. So we're going to go over some habits again. Okay, fibrous, bellated, cubic. Here's another example of banded agate. And then we have streak. So streak is something that remains the same for a specific mineral no matter what color it is. Here we have two different types of hematite. One is very red, one looks gray. So remember, hematite is something that we'll see in stores that has been magnetized, and they turn it into these cool little magnetic beads that you can buy, right? Both of them, even that magnetic stuff, if you scratch it on a scratch plate like this, it will always have that reddish brown streak, okay, no matter what. And then we have fluorescence. So fluorescence and thermoluminescence both have to deal with minerals' ability to absorb and reflect UV light. Okay, and I mean that as in black lights. Fluorescence occurs when the mineral fluoresces under UV light, whereas thermoluminescence, the mineral will actually absorb the UV light and glow for a period of time after the UV light is taken away, which is cool. So what we have here is actually willemite, which is this green stuff, franklinite, which is the black, and calcite, which always fluoresces red. Okay, so here we're going to see more in the form of habits. Again, dodecahedron in the form of garnet, and prismatic in the form of quartz. And here we can actually see some of those little C's showing the conchoidal fracture of quartz. Again, if you have two massive pieces, one of quartz, one of fluorite, always look for the little C's. That will tell you which one is quartz. Effervescence is when a mineral bubbles when you put hydrochloric acid on it. Okay, this means it is calcite or some sort of related calcite mineral. Okay, it also happens if you have a rock that has calcite in it, or a rock that is a conglomerate of carbon-based material. So for example, seashells will bubble with HCl because they have carbon. So what about piezoelectricity though? We didn't really talk about that. And so piezoelectricity is something that is unique to quartz. And so if you hit two quartz crystals together in the dark, they'll make a small flash of light. And it will make the smell of burning. And it's actually pretty cool. Again, only unique to quartz. So I'm going to try to show this to you in class if I can get big enough quartz samples, because if in the dark you can accidentally hit your fingers together. But you can go ahead and look it up on YouTube. Sometimes there are some good videos out there, sometimes you can't. But it is really, really cool. And that is the end of our lecture. I will see you all in class next week when we will go over rocks. And I hope you enjoyed this lecture. I'm sorry that we couldn't do it in person. But when we have our next lab, when we talk about minerals, we will be looking at all of these again and talking about these habits. All right? So I hope you have a wonderful day, and see you later.